supposed to stand on? Am I okay? I'm supposed to wait. Good. Okay, I can hear myself too. Great. Well, thank you all for coming and for attending the talk and attending the workshop. My name is Steve Dodge, and I'm going to be talking about how excitation fluence can be used as a tool for understanding photoexcited Mott insulators, as well as superconductors, which is something that I hadn't originally intended to talk about. But we've gotten some very, I think, important recent results that recent results that I think will be of importance and interest to all of the people who are here for the workshop. I want to start with the acknowledgments. There were a number of people who were involved in all of the work that I'm going to be talking about. I'm going to start from fairly early on, so I'm including some previous graduate students, as well as a number of people who made materials. But the two people who really did most of the work here are Derek Sahota and Leah Lopez. Derek finished with me in 2019 and as a PhD student, and Leah is currently with me as a PhD student. And so I'm going to be talking to you about three different ways that we've examined how fluence interacts with solids. And the message that I want to convey to you is that and when we do time-resolved spectroscopy, I think, one of the first things that we focus on is the time degree of freedom. And so, that's obviously something that we're interested in extracting information out from. And fluence is, people use it as a tool, but I think it's an underappreciated tool. And so I'm going to try and convince you that we should be paying more attention to this. And so I'll start with Terahertz Photoconductivity, which is what sort of brought us into this. I was interested originally in just sort of, okay, if you take a Mott insulator and you photoexcite it, what happens to the carriers? Because there's this paradigm of what happens of how quasi-particles move in equilibrium in charge transfer insulators like the cuprates here, where if you create an electron in a hole through light, you transfer a hole. This is in a hole picture. So the hole gets transferred from the copper orbital into the oxygen orbital, as Matteo was discussing. And then that now forms a singlet, which can hop. And so that now is free to move around. But of course, as it does so, it leaves misaligned spins. And so it's not immediately obvious that that is a free carrier, because there's an energy that it's gaining or that it loses, I should say, as it moves away from the what I'll call the doublon, which I've represented here in pink. But when you photoexcite it and you probe with terahertz, it turns out that you can see a clear photoconductivity signal. It's relative over our bandwidth, which is out to about 4 MeV. These are very basically flat. So you're basically just looking at what is, if you extrapolate to 0, you're just looking at like the DC conductivity as a function of time. And we, at a fluence of about a quarter of a millijoule per centimeter squared, which is about a little bit less than a photon per copper, we can then look at the total amount of photoconductivity by just looking at the height of that peak, which in this case is just the change in the electric field in our terahertz signal, which we can then convert into a conductivity using the expression above. And this expression at the very top is one that we've been using to fit these curves, because one of the first things that you see when you study these things is that the dependence on fluence is sublinear. And that sublinearity, we can call it saturation, but it's not immediately obvious from looking at the plots that it is going to saturate at some fixed value. You can still fit with a form that's shown at the top there. So you have a fluence in the numerator, you have a fluence in the denominator. At low values of the fluence relative to f naught, then this is just linear. But as you approach higher and higher values of the fluence, when f is much greater than f naught, then everything basically approaches a constant asymptotically. And so we use this actually in order to extract out get a better fit to the low fluence region, because the signal is weaker there. And you want to go to the higher fluence area in order to get the signal stronger, but you're stuck because now you have this nonlinear dependence. And so we use this fit in order to extract out the numbers that you see at the bottom for the mobility, which is the thing that we were after. And we see here that the mobility in strontium copper oxychloride, fairly standard canonical charge transfer insulator that's like, like many of the cuprates, but it's hard to dope, so it's actually good for optics because it's relatively clean, as well as YBCO6, which are samples that we got from Ruxinglang. And both of those are, they're of order a centimeter squared per volt second, which is comparable to what people had observed previously in Hall measurements in equilibrium. So the answer to my original question in this is that yes, when you photoexcite carriers, they actually are mobile. They don't get stuck, or, they don't form excitons. They're at least not initially. They are free to move around. And in principle, you can then manipulate those carriers just as you would, you can think about them just as you do equilibrium carriers, except that they only last for a picosecond or so. So then we moved to studying, well, why does this happen? Why does this saturation occur? And for that, you want to understand the kinetics of the carriers. And there's an interesting story here, because one of the things that, here I'm showing you three different, basically this is pump probe, where we're pumping at the black arrow in the upper left-hand corner there. Well, let me see if I can sort of get this into a mode where I can show you with my fancy, with phone pointer. So we're pumping, at basically double the Ti-Sapphire frequency. And then we have three different samples here, which are indicated by the legend down here. So we've looked at LCO, strontium copper oxychloride, and YBCO6. And you can see that the charge transfer gap is different for all of those three. But if you shift the energy scale by the value indicated by the markers, then the pump probe signal that you see in the change in the reflectance relative to the average, to the equilibrium reflectance, all lines up perfectly. And what that is associated with is basically a shift downward. Here we're in a totally different regime from what Matteo just talked about. We're above the gap, and so we're creating real photocarriers. Those photocarriers then renormalize the gap, potentially just by screening, but also potentially by giving off phonons, which also screen the gap. So it's a little bit unclear, I think, experimentally, which of these is dominant, but both are probably playing a role. And so then you can see at the lower plot that this signal decreases on a time scale that's sub-picosecond. And that's the puzzle. How can you give off, look at the energy scale here. There's 1 eV of energy, and you're giving it up in, giving up 1.5 eV, or 1 to 1.5 eV in less than a picosecond. And if you are giving that up to phonons, say 50 MeV phonons, then you've got a lot of phonons to give off in a very short period of time. And so that remained a kind of a question mark for a long time until the work of Lenarchik and Pralovchik, which considered the case actually of an exciton now. So this is, it's in the original scenario was in tension with what I just told you, that they're free carriers. But if you set that aside for a moment and consider that you have a holon and a doublon that have been created by light, and then you have a hopping process where you go around the corner there. This is a cartoon. They did it quantum mechanically with all the details. And what you do, what you'll notice when I did that hopping, is that I now broke 8 bonds. And if you assign an eighth of an EV to each of those bonds, you've got an EV of energy that you've just given up in that process. And so you have a way to give off a lot of energy through magnon emission through just one single process. And so it's much easier to imagine that you could give off that energy in a short time scale. Now, the question remains, okay, that scenario works if you already go into an exciton state. And I've shown you that the original carriers are free. And so this becomes a problem of basically carrier kinetics that we wanted to then study. And so what we looked at was that here I'm showing you the change of the differential reflectance on top. And I'm looking at the initial scattering rate for gamma for the 3 different compounds, all as a function of fluence. And so you can see that all three of the materials saturate with fluence, and all 3 of the materials have some dependence of the initial rate on fluence, but they go in different directions for different materials. And in YBCO, it's basically flat. And that is not what you would expect for recombination through into an exciton, because electrons and holes have to find each other if they're going to recombine that way. And so that's known as bimolecular recombination, where you expect that the rate will be very sensitive to the total density. So that was a puzzle, which we sort of puzzled over. And we looked at a variety of different pump wavelengths, all shown in the legend on the left here. You see that they all fit to this, this saturation form that I've showed you earlier. And I'm showing, this is for YBC06, and the time scale here, or I'm showing two different rates, or two different curves, superposed on top of each other, one at well below the saturation fluence and one well above it. So the fluence dependence is virtually, it's basically unnoticeable in this material. You can see a little bit of a difference in some of the other materials. And so this behavior was studied in this kind of problem was studied in semiconductors in the 50s, and it's known, it was explained by Shockley, Reed, and Hall as a mechanism where you can, if you have a trapping center, then you can have a single carrier go into the trap, and then it can recombine with another carrier at another time, and those are independent processes, and now you've gotten around the bimolecular recombination problem. You also have Auger recombination, which is a density-dependent effect. And if you have these two things in combination, then you can get the saturation, you can get the fluence independence of the rate, and everything works out. We've excluded bimolecular in this, the sort of naive bimolecular, but I should say that what I'm going to show you next, basically it's any kind of many-body recombination can occur, so long as it's occurring in parallel with a trapping process that's very, very fast for one of the carriers. So the idea here is that the only way you can get this to work is that if the trapping for one of the carriers is essentially the trapping time is shorter than your pulse width, because what you can get then is a case where as you're cranking up the fluence, this corresponds, let's say, to the doublon, and this to the holon. So if the doublon trapping rate is very fast, then it grows and shrinks essentially with your pulse width. And if you crank up your fluence, then the overall magnitude of that peak will change. And so the initial Auger recombination rate represented here in these rate equations will grow and shrink, but it only lasts as long as the pulse lasts. The minute the pulse goes away, most of your electrons, or your doublons, have trapped, and now what you're observing is essentially the holon decay rate. And so it's a single particle decay rate, and so it's independent of fluence. We've then modeled this. This is, again, YBCO. These are experiments. This is a model that we developed. And one of the things that you notice here is that the leading edge shifts to earlier times. That's a distortion effect. Basically, as it saturates, the peak is getting flattened. Everything else is coming up at the same time. And so the shape of the peak is changing. And so if you're looking at the the leading edge, as the half width of the half maximum, then you think that it's moving moving earlier, but really you're just flattening the top of the pulse, and you're just changing the shape. Okay. One last thing about this, YBCO and LCO, all of these materials are a little bit different, and what we see is that in early times, this saturation occurs, but then in some materials, we have observed that you can see a change at longer times, but it becomes linear in the fluence. And so what we interpret this as is we have carrier recombination. There are sort of two components to the spectra, one of which is sensitive to the carriers, the charge carriers, and the other which is sensitive to the bosonic degrees of freedom. And so as the carriers are, in this regime, the carriers are dominant, and then as they give off their energy to the bosons, then we start becoming more sensitive to that. And so this is basically, we've scaled these so that they all have the same slope, and at the peak it saturates, and in the tail it's just linear. So with this, I now want to get you, once we, worked all of this out, there was an insight that we had that we then have applied since, very recently, to experiments on photo-induced superconductivity that I want to tell you about. And it's a general issue that I think everyone who does pump probe spectroscopy needs to know about, and I think has not really been fully appreciated until now. So I'm showing you results that are basically taken from a paper by Budin et al., where they conveniently published all of the raw data so that we could just pull it out and put it in a plot rather than going and digitizing it. And I want to walk you through the, let me check the time. How am I doing for time? What's the, 5 minutes? Perfect. Okay. Just want to walk you through the reasoning that goes into this data. The raw data is basically what I'm showing you is, what this shows is a transformation from raw data, which I'm representing as delta R over R, and R bar, which is the equilibrium reflectance, and alpha, which you take from measurements. Basically, that's the attenuation coefficient. And then you take that information, you convert it into a photoconductivity, delta sigma, and then an equilibrium conductivity, which you get from Kramers-Kronig transformation of the reflectance. Now, with that information, you get the conductivity. Here's the equilibrium conductivity and the photoexcited conductivity at 1 picosecond after photoexcitation. And then with that information, often what is reported, and this is done for convenience to compare with equilibrium reflectance measurements, what is reported is the reflectance of a fictitious medium. It's important to understand this, and it's not all, because there are a lot of things going on in these papers. It's easy to overlook that this reflectance that's being reported is actually for a medium where the surface conductivity is assumed to penetrate homogeneously into the sample, and then that's what is then being reported. The actual photoconductivity is shown in green here, which we've just backed out from the inverse process that I've represented up here. And the reason for the difference is that you have, here is the pump profile, here is the uniform profile, and here is the probe profile. And in most cases, your pump probe that have been studied, the pump profile is at least smaller than the probe profile, and in many cases much smaller. And this is an issue because when you think about what happens when you saturate the medium locally, what you're doing is you're distorting the depth profile. And so if you're assuming an exponential decay, then as it saturates, the effective thickness of your medium increases logarithmically. Logarithmically because it's an exponential decay into the medium and you're saturating with linear fluence. And so when you can use a different form for the conductivity, which I represent here, now here, this is the same saturation form, but now with an exponential decay, and where we're assuming here that the local photoconductivity, delta sigma, is proportional to the energy density of the pump as it penetrates into the medium, and we're assuming further that the energy density of the pump decays exponentially with the equilibrium decay rate, which again is an assumption, and you're pumping these things pretty hard. So I think that's an assumption also worth questioning. The orange shows what we have assumed as the actual local photoconductivity as a function of fluence in units of a saturation value. And if you then back out what you would get if you assumed an exponential decay for the specific case of one of the lower frequencies that I showed you for Budin et al., then you get the blue curve here. In the limit of, in the long wavelength limit, this curve, you basically approach the log of 1 plus f. Okay, that's an exact solution. And then what I show you here are points that are taken from the work of Metrano et al. In 2016, where we've basically scaled them in the horizontal and in the vertical direction to match that axis. And so you can see the agreement is quite good, and the chi-squared, if you do this with their error bars, is perfectly consistent with that form. We've also done this for LBCO, and this is where there's published data on the fluence dependence at 0.8 microns. You see that the data is quite scattered, but if you draw the expected distorted fluence dependence through those points, then you get that curve. And if you do the same thing for 2 micron pump, then you get that curve. And so the saturation fluence is quite different for these materials. And so if we take the reported values at 0.8 and 2, represented by the solid lines, and then rescale them according to what we expect them to be in the local photoconductivity actually, then you see that here there's not much change anyway, but in sigma 2, you go from 0.8 microns being much larger than the 2 micron data to basically lying right on top of it. So we take that as good evidence that this effect is playing an important role in many of the experiments that have been reported on photoinduced superconductivity. If we now take a saturation form where we just assume that that you go to some saturated value of a Drude peak with some unknown value of the Drude scattering rate, then what we can do is we can fit the distorted value of the curve under these assumptions to the published data. And what you see is that the actual value lies significantly away from the distorted curve. And if you extend it out to lower frequencies, what you find is that the scattering rate of the saturated value is significantly smaller than the equilibrium scattering rate, but smaller by a factor of order 10. Another way of thinking about this, which in many ways makes more sense, is to assume not that the conductivity itself is going from an equilibrium Drude peak to a saturated Drude peak, but that the rate itself is changing with fluence. And that's actually a different functional form. And so we've fit to that as well. And in that case, we've chosen to fit both the data from Budin et al. At 3 millijoules per centimeter squared, as well as the reported results by Butzi et al. At 4.5 millijoules per centimeter squared. And what we find there is that because of this distortion effect, as you crank up the fluence, of course, sigma 1, which is decreasing as you reduce the scattering rate, the actual local photoconductivity, the actual local conductivity never goes negative, but the distorted real conductivity, I should say, actually goes negative. And this is exactly what was observed by Butzi et al. And was talked about yesterday by Daniel Podolsky using a theory that he developed that I think is a wonderful theory. It's a very elegant idea. I think this result, though, calls into question whether it applies to this particular compound. When we do this fit, we find that the saturated value is 0. The rate is 0. But the surface values are different from 0. And so the surface value at 3 millijoules per centimeter squared is about 1/8 of a millielectron volt. And at 4.5, it's about 1/6 of a millielectron volt, rounding up. There's one case that is worth mentioning in this context, which is the charge transfer salts. And in this case, the authors of all of these papers, many of whom are in this room, were well aware of this issue. And so, they did this experiment where they chose to get the pump penetration depth longer than the probe. And this remains something that we can't explain. I mean, there's saturation here as well, but this distortion effect is much weaker in this case. And so these results remain, they're less affected. However, all of the cuprate results in the K3C60, I think, need to be re-examined. So with that, I'm going to just put up my conclusions. The photocarriers, fluence dependence, the bottom line is fluence dependence is important. It's worth paying attention to. When you see saturation, don't ignore it. And the photocarriers in insulating cuprates are mobile. They exhibit recombination, and the mechanism for the saturation, we think, is due to a combination of Shockley-Reed-Hall and Auger recombination. And I didn't mention this, but the recombination coefficient that we obtain from our fits is 1,000 times larger than gallium arsenide. And so there's a hint here that strong correlations are playing an important role in the many-body recombination process that's leading to the saturation. And so then through this exercise, we learned something about how to understand photoconductivity results as you measure them in conventional measurements. And I think that leads to, it suggests that there's a photo-enhanced mobility in K3C60 at least, but it argues against photo-induced superconductivity in that particular, at least given the examples that we've seen so far. So there's much more to learn, and I've given you a couple of references for the old work. The newer work is coming out soon.
Thank you very much.
Yeah, thanks, Steve, for this very nice and clear talk. So I have the benefit of having discussed this with you yesterday at lunch and having slept over this and going through the notes of the group meetings from Matteo's PhD thesis.
Yeah, great.
The reason why what I think you're saying is either not right or not unique is that when we were thinking about this problem, we were considering an effect that depends on the electric field.
Yes.
And not on the fluence. So if you're
right.
considering either a phononic effect or a Floquet effect, then a square root growth in the fluence is a linear growth in electric field. And if that were the case, which of course I don't know, if it's the underlying physics is an electric field effect, then what you're saying is not right.
Can I stop you there?
No. The second thing that I'm going to say before
May
you
I
answer...
ask the chair to moderate this discussion
Chair, can I say one thing? The other thing that I should mention to inform the conversation is that the effect of saturation in fluence only happens at the earliest times. When you look at the metastable state, the metastable state is linear influence, and of course you don't know this because the data is not published, but I'm informing you of this now.
Yeah, okay, good.
So all I'm trying to say is that it's not clear to me that what you're saying is positively wrong, but that there's more than you are in the analysis that you're implying. That's what I wanted to, Thank you for the heads up.
I'd love to hear more about unpublished results. The one thing that I do want to say in response to your comment about the square root effect, if you look at that blue curve, it's very difficult experimentally with the error bars that are shown, both here and the square root effect is something that for those who are not aware of this, I've been staring. They've been writing these papers. I've been staring at them. So let me just back up. There's many of the YBCO papers and the cuprate papers generally are represented where they show basically the superfluid density, which they extrapolate from sigma 2 from a fit to sigma 2. They show that as a function of electric field, and that is approximately linear. It doesn't go exactly through 0, but it fits that it fits something like a square root form. If you convert that to fluence, it's very difficult to tell the difference between that and this logarithmic effect that I'm showing you here.
No, but the important point is that if you believe that the interaction is not one similar to exciting photocarriers, but has to do with the excitation of a phonon or some low lying, then the extinction depth will be linear in field, and hence the saturation will not happen. Now, whilst I don't know which one of the two mechanisms, so it might well be that you're right, there's more in this than you are purporting it to.
Okay. This is actually a very important point that I want to emphasize. What I'm saying here is completely independent of any microscopic mechanism whatsoever. It is entirely, the minute you see anything that is sublinear in your signal, this is important.
But that's not true because you're assuming that it depends on the square of the field.
No. No.
Look at it. You plot it as a function of fluence. If you plot it as a function of field, it's linear. And then we can all go home. And of course, I don't know which one of the two it is. But,
Okay, then let's basically go back to this. Oops, I'm going the wrong way. You agree that this is the expression that you're using to determine the surface photoconductivity. That's the functional form that you fit to.
Yeah,
and hold on.
What is alpha? Is that field alpha or fluence alpha?
Stare at that functional form. I invite everybody to look at that functional form and recognize that there's an implicit assumption embedded in that expression that the change in the conductivity is directly proportional to the excitation density. So you have already assumed the thing that you're saying I shouldn't assume.
Density doesn't exist in my language.
I think we can continue this discussion after the break. So already we are behind the schedule, so I'm afraid we have to move on. So thank you again, Steve.